Hello and welcome to Algebra 1, Lesson 1. In this lesson, we're going to learn about variables and expressions. So now that we've completed our pre-algebra course and we have a great command over arithmetic, we're going to move on to some tougher material. Now, generally, when you finish a pre-algebra course or when you first start an Algebra 1 course, you begin learning about something known as a variable. Okay? So what a variable is, it's a symbol, generally a letter, and it's going to be a lowercase letter, used to represent an unknown quantity. Okay? Another way you can kind of think about this, it's going to be a placeholder. So I put here that x, y, and z are the most commonly used in algebra. But you can use any lowercase letter that you want. Just for right now, these are the ones that you're pretty much going to work with. X, y, and z. All right, so here's some examples. So Mark works at a car wash and earns $63 per day plus tips. So if I wanted to kind of model this mathematically and say, how much does he earn every day? Well, I know that he earns $63 at minimum, right? $63 per day. So let me start by putting $63 down. Now we have an additional amount. We have this keyword here that says plus, and then we have tips. We don't know what the amount of tips is going to be, right? Just like a waiter or anybody who works in the service industry that gets tips, you don't know what you're going to get in tips that day. You might get a customer that overly tips or a customer that under tips. So that amount's going to vary. So we can represent this unknown with a variable. So I'd put $63 plus, and let's use the common variable of x. So plus x. So this represents the amount of tips. Now, we can use this to model what this person Mark is going to receive every day. He gets $63 plus x, where x equals the amount of tips that he's going to receive. So let's say the day is over and he knows that he got $7 in tips. So x, in this case, would equal 7. If I want to know how much he made for that day, all I would do is I would take this right here, this 7, and I would plug it into the x right here because x equals 7. He got $7 in tips. X was the amount of unknown tips he was going to get. And so we plug in a 7 for x, and we'd end up with $63 plus 7, and I'll put dollars there just to be consistent, and this will equal $70, right? That's how much he received for that day. But the next day, it's going to be different. So let's say the next day, x is going to equal 9. Well, then I'd take 63 and I'd add 9 to that, right? I'd make $2 more, or I'd have 72. So the following day, you would have $63 plus, and let me do this in a different color so we don't get confused, $9, right? So in that case, x is equal to 9. So we see that as we change the value for x, the value is going to change. In this case, x is equal to 7. I plug in a 7 for x and I get 70, right? 63 plus 7 is 70. In the other case, x equals 9. So I plug a 9 in for x. 63 plus 9 is going to give me 72. So he earns $72 in this case. Let's take a look at another one in case you're a little confused. So a gallon of milk costs an unknown amount. Jason wishes to purchase 2 gallons. Well, again, we can use a variable to model this situation. So I know that he's going to buy 2 gallons. So that's 2. And it costs an unknown amount. So I can use a variable. Let's use y in this scenario to represent that. So I need to multiply the cost per gallon times the number of gallons. The number of gallons is 2. The cost per gallon is unknown, so I would have 2 times y, which we're going to write as just 2y. Okay, when a number is next to a variable, it implies multiplication. So 2y like that is telling me that I have 2 times y, or 2 times y. You remember back in pre-algebra when I said we stop using this symbol to imply multiplication, and the reason is because it often gets confused with the variable x. So we'll either use this symbol, or we'll use parentheses, or we'll place the number next to the variable. And this is the most common. You'll just have 2 times y like this, just 2y. That implies multiplication. Now, if I give you a cost per gallon of milk, I can tell you how much Jason's going to spend on his milk purchase, right? If I say that y is equal to $1, and I'm not going to put the dollar symbol in this time, I'm just going to put 1, well, then really all I'm going to do is plug a 1 in for y, right? This is the unknown cost per gallon of milk. If I tell you that it equals $1, I could just plug a 1 in there, and I can say, okay, well, 2 times 1 is 2. So 2 times 1 is 2. So he spends $2 on 2 gallons of milk. If that amount changes, right, if I say, well, the price of milk just went up. So let's say that now y is going to be equal to 3. Okay, we had a big price increase. Well, now I'm going to plug in a 3 for y. So instead of 2 times 1, I would have 2 times 3, and that's going to give me 6. So now he's going to spend $6 on 2 gallons of milk, right? And that makes sense. 2 times 3 is 6. So if Jason buys 2 gallons of milk at $3 per gallon, he spends $6. In the other scenario, if he buys 2 gallons of milk at $1 a gallon, he's going to spend $2. All right, so let's get into some more kind of definitions. A term is a single number, variable, or a number times one or many variables. So for example, you might see something like 4x. Okay, that's a term. Or you might see something like 9y. That's a term. Or you might see something like 24x, y, z. Or you might see something like -3a. These are all examples of a term, right? A single term. Again, it's a number by itself. So if I just had, let's say, the number 7, that's a term. Or it's a number times one or many variables. So in this case, you have one variable, one variable, one variable. In this case, you have many variables. And these variables can be raised to powers. So for example, I could have had an example of a term where I have 24x squared y to the 4th, z to the 8th, let's say n to the 12th. That's a term, right? A single term. Now here's another kind of definition thing. When a number is next to a variable or variables, it is known as a coefficient. So in all these scenarios where I'm saying, okay, 2 times y, right? 2y is how we would say it, but 2 times y really because it's multiplying. 2 is the number that's multiplying the variable y. It's known as a coefficient. 2 is the coefficient of y. If I had, let's say, 4x squared z, 4 is the coefficient, right? It's the number that's multiplying the variable, or again, variables if you have more than one. So this is, again, a coefficient. And these are kind of very basic definitions that even if you don't get them in this video, you can write them down and put them on flashcards if you want. We're going to talk about them over and over and over again. By the time you get to the 10th lesson, you will know all of these terms, right? It won't be an issue for you. All right, so a number that is hanging out on its own is known as a constant. So you're going to get to a point in this lesson where we start talking about algebraic expressions, and you might see something that looks like 5x plus 7. So this number, this 7 that's hanging out by itself, is a constant. This is a constant. Its value is not going to change. It's what we've worked with in pre-algebra, right? Where we're just doing basic operations. If I do 7 times 3, that value is always going to be 21, right? It's not going to change because we're working with constants. If I have 5x plus 7, well, I don't know what the value of x is. Again, it's allowed to vary. It's allowed to change. And so the value for this is going to change based on what x is. If I change x, I change the value of this whole algebraic expression. So that's kind of the difference here. That's why we say this is a constant, because the number 7 is not going to change. If I have something like 3x squared minus 2. 2 is hanging out by itself. 2's value is constant. It's not going to change. So that's why we refer to it, again, as a constant. All right, so here's a pretty important definition. An algebraic expression is one or more terms separated by plus or minus symbols. So again, your terms in an algebraic expression are separated by the plus and minus symbols. Very important. So let's look at an example. Let's say we have something like 5x plus 2y minus 4z. So if you want to look at that algebraic expression and say, where are the individual terms? Well, every time you see a plus or a minus sign, you've cut off a term. So this is a term, this 5x, because there's a plus here, right? That cuts off this term from this term. Then this 2y is a term, right? You have a minus sign here, and you have a plus sign over here. So it kind of separates everything. Let me just kind of draw a line here in a different color. This kind of separates everything. And then here, where you have 4z, again, that's a term. So you have 5x, 2y, and 4z that make up the terms here. And it's called an algebraic expression because there are variables involved. If you just kind of have numbers involved, we just refer to that as an expression. Right? So if you had something like, 2 times 3, that's an expression. Right? We work with that in pre-algebra. So 2 times 3 is 6. All right, so the main thing about an algebraic expression is that the value will change as its value given for the variables involved are changed. So let me give you some examples. Let's say we had something simple like 2x plus 3. And I say I want to let x equal 4. Well, what I'm going to do is everywhere I see an x in the algebraic expression, I'm going to plug in a 4. So I'm going to take this value and plug it in here, everywhere I see an x. So that means that I'm going to have 2 times 4 plus 3. And again, I can put parentheses around 4 and put it next to 2, and it implies multiplication. Remember, 2x is the same as 2 times x. So when I replace x with 4, I'm still going to do the multiplication operation. But now, since it's not a variable, it's a number that I replace the variable with, I can just calculate it, right? 2 times 4 is 8. So this would be 8 plus 3, and then 8 plus 3 is 11. And again, I did the multiplication first because of the please excuse my dear Aunt Sally, right? Remember your order of operations. This is where you're really going to use them. All right, so let's say we change the value of x. Let's say we want to let x now equal, I don't know, let's say 5. So instead of plugging in a 4 for x, now I'm going to say, well, 2 times 5 plus 3 is going to equal what? Again, I'm plugging in for x whatever value I let x equal. So that's why there's a 5 there. And so we just calculate. 2 times 5 is 10, then 10 plus 3 is 13. Right? And I did that in one step versus 2 up here. Hopefully you can follow, right? 2 times 5 is 10, then 10 plus 3 again is 13. So as I change the value of x, the value of the algebraic expression will change. Let's do one more. Let's say, again, 2x plus 3. Let's let x equal negative 2. So I'm going to plug in a negative 2 for x, right? Very, very simple. So 2 times negative 2 plus 3 equals what? 2 times negative 2, remember, positive times negative is negative. 2 times 2 is 4. So that's going to give me negative 4, then plus 3. And at this point, we know how to add integers, right? Negative 4 plus 3 is negative 1. All right. So again, in each case, we got a different value for the algebraic expression because we chose a different value for our variable x. So in some cases, we can simplify an algebraic expression, and we're going to do this using the distributive property. So we learned this back in pre-algebra, and to give you a basic reminder of this, let's say we had something like 3 times this quantity 6 minus 3. Again, because we have parentheses here, I'm basically saying what is 3 times the difference of 6 and 3? right? So 6 minus 3 is what? That's 3. So 3 times 3 is 9. But we can use the distributive property to do this as well. Remember, because multiplication is distributive over addition or subtraction. So what I can do is I can distribute the 3 to each term inside of the parentheses. Remember, if I have a single number, that's a term, right? A single number, that's a term. So 3 times 6 would give me 18, but let's write it out like this. And then minus, you'd have 3 times 3. 3 times 3. I'll get the same answer as I did before, right? I'm going to get 9 either way. 3 times 6 is 18, and we're subtracting away 3 times 3, which is 9, and 18 minus 9 is 9, right? So either way you do it, you get the same answer. So we're going to use that property here to simplify. We have 3 times this quantity, x minus 4. So what I'm going to do is I'm going to distribute this 3 to each term inside the parentheses. So 3 times x is 3x, then minus 3 times 4, which I can write 3 times 4, I can just say 12, right? We know that's 12 at this point. So I've simplified 3 times this quantity, x minus 4, as 3x minus 12. Now, I don't have a single number here as an answer because I still don't know what the value of x is. But I've simplified it a little bit, or some people in some cases are going to want to write it this way. And we'll learn about that later on in Algebra 1, where we're going to reverse what we just did. That's a process called factoring. And again, we're not going to talk about that now. That'll be in a much further lesson. All right, let's take a look at another one. We have 4 times the quantity x minus 7 plus 2. So what I'm going to do is I'm going to multiply 4 times x. Right, I'm going to distribute. So that'll be 4x. And then we'll have 4 times 7. That's 28. And then plus 2. So at this point, I don't know what 4x is, right? I don't have a value of x. But I do know what negative 28 plus 2 is, right? I can do that. And again, if I have minus 28, that's the same thing as plus negative 28. So that's why I said it that way. So negative 28 plus 2 is going to give me negative 26. So we would have 4x minus 26. All right, now let's talk about like terms. So like terms are terms with the exact same variable, or variables if there's more than one, that have the exact same exponents. All the variable parts have to be the same. I can't stress that enough. So for example, 5x and 3x are like terms. It does not matter what the coefficients are, right? Remember, that's the number that's multiplying the variable, or again, variables. It only matters what the variable or variables are. In this case, we have x. In this case, we have x. It's the exact same variable, and so we have like terms. Let's look at 5x and 3y. I have x, and then I have y. Those are not the same. Not the same, right? They're different letters, so they're not the same. And so we do not have like terms. These are not like terms. What about 2x and then 3x cubed? Well, they both have the variable of x, but they're not raised to the same power. That's got to be the same. Everything has to be the same. So this stops it from being like terms. So these are not like terms. Not like terms. What about here? We have 7x to the 4th power, 4y to the 4th power. Well, we have the same exponent. Notice how we have each variable raised to the 4th power. But the variable itself is different. One is x, one is y. You can't have anything be different. Again, the coefficients can be different. 7 or 4 or whatever the number parts are, that can be whatever. The variable part has to be the same. And in this case, it's not. This is x, this is y. They're different, and so they're not like terms. Here we have 3z squared x and then 2xz squared. So this one might look like they're not like terms, but in fact they are. The variables are presented in a different order. But I want you to remember back from pre-algebra that multiplication can occur in any order, right? That's called the commutative property of multiplication. So if I have 3 times 2, that's the same as 2 times 3. In each case, it's 6. So I can multiply variables in any order. I can have z squared times x or x times z squared. It doesn't matter, right? So I have the exact same variables here raised to the same power. I have z squared and z squared. So put a check mark there. And then I have x and x. Put a check mark there. And again, the coefficients can be different. So because everything is the same, we have like terms. Like terms. Okay, so let's talk a little bit about what we're going to do with these like terms. All right, so when we combine like terms, the variable part stays the same. So if I have x squared and x squared, that doesn't change. We're just going to be adding and subtracting the coefficients, or again, the number parts. All right, so let's take a look at 2x plus 3x. Nice and easy problem. I want you to imagine if you had 2 oranges and you added to that 3 oranges. Well, everybody knows they'd have 5 oranges. The easy way to do it is just to leave the variable the same. Just say, okay, I know I'm going to have x, and just add the coefficients. So 2 plus 3 is 5, that's 5x. If you were to visualize what's going on, 2x is x plus x, so x plus x. And then 3x is x plus x plus x. And if you kind of view it this way, it makes sense. Okay, I have 1, 2, 3, 4, 5 of these guys, 5x. But you don't want to do that every time. It's going to slow you down, right? So you just want to say, okay, the variable part is going to stay the same. So that x is going to stay the same. So I just write that first. Then I'm just going to add the coefficient parts, right? So 2 plus 3 is what? That's 5. So I end up with 5x. And again, if I have 2 of something plus 3 of the same thing, I'm going to have 5 of something. So 2 apples plus 3 apples gives me 5 apples. 2 Honda Civics plus 3 Honda Civics gives me 5 Honda Civics, right? So on and so forth. Another way to kind of think about it, using the distributive property, and it involves factoring, which we haven't gotten to yet, but if I were to write this for you like this, let's say that I pulled the x out, which is common to both, and I wrote this as x times the quantity 2 plus 3, well, I could do 2 plus 3 first and get 5, multiply 5 times x, and end up with 5x. Or I could, again, distribute the x. X times 2 is 2x plus x times 3, which is 3x. And again, you see where we start with this 2x plus 3x. So kind of any way you want to use to visualize what's going on here, it's 2 of something plus 3 of the same thing is giving you 5 of that thing. 2 apples plus 3 apples, 5 apples. 2 oranges plus 3 oranges, 5 oranges. So on and so forth. Here we have 2x plus 3y. Now, we don't have like terms here, so we can't combine them. So let me try to make sense of this for you. If I have 2, let's say, oranges, and I try to add that to 3 apples, well, I still have 2 oranges and 3 apples, right? I can't combine them and say, okay, well, I have 5 orange apples, right? I don't. In the case where we had the same variable, right, we had like terms, well, yeah, I'm adding the same thing. So if I have, again, 2 oranges plus 3 oranges, I have 5 oranges. If I have 2 apples plus 3 apples, I have 5 apples. But if I have 2 oranges plus 3 apples, I just have 2 oranges and 3 apples. So there's no way to kind of, combine these. It's still going to just be 2x plus 3y. So if you don't have like terms, you really can't simplify, right, in this scenario. All right, here we have 4x squared plus 3x squared plus z. Now, look for your like terms. I have x squared and x squared. So these two are like terms. These are like terms. And so we can combine them. And I missed an r there. The z is not common to anything, right? So we're not going to have like terms with just the z. So what you do in this scenario is you just combine what you can. So 4x squared plus 3x squared, again, leave the variable part the same. So leave that x squared part the same, and then just add your coefficients. So what is 4 plus 3? That's 7. So I have 7x squared, and then just copy the rest, so plus z. So when we simplify this algebraic expression, we end up with 7x squared plus c, right? Again, you combine what you can, right? In this case, we could combine the like terms 4x squared and 3x squared. All right, here's one that's a little bit more challenging. We have negative 2 times the quantity 4x minus 7 plus 4 times the quantity x minus 3. So the first thing I'm going to use is the distributive property to kind of simplify this a bit. So I'm going to multiply negative 2 times 4x, and that's going to give me negative 8x. And then I'm subtracting away negative 2 times 7, which is going to be negative 14. Now, I'd end up with minus a negative 14, which is the same as plus 14. Now plus, I'm going to do the same thing over here. We have 4 times x, that's 4x. And then minus 4 times 3, that's 12. And so now we're going to look for like terms. So I have negative 8x and 4x. Those are like terms, right? The variable is x, right? There's no power. You can think of the power as being 1, right? So in each case, you have the same thing. And then you have 14 and negative 12. Those are just numbers or constants. Those can be combined. So let's start out with just negative 8x plus 4x. Well, the variable is going to stay the same. So that's just going to be x. And then think about the coefficients. So what is negative 8 plus 4? Well, negative 8 plus 4 is going to give me negative 4. So this is going to be negative 4x. And then I'm just going to combine the number parts. So I have 14 minus 12. That's going to give me 2. So plus 2. So the answer here would be negative 4x plus 2. And I can't simplify this any further because I don't know what the value of x is. So I can't combine this with 2, right? I can't really simplify this unless you give me a value for x. If you said, hey, let x equal this, then I could give you a value for the algebraic expression. But without that, I'm kind of stuck here.